Audiobook What is Light? Wave Theory of Light and Origins of Ether in Science by Majid Fekri. Chapter 6, page 41. Newton's Corpuscular Theory of Light. Newton became interested in optics at a young age. In 1666, when he was 23 years old, he bought a glass prism to study the colors of light. He darkened his room, made a hole in the window screen to allow sunlight through, and put his prism to work. He was convinced that the white light is composed of different colors and that prisms can separate them because each color of light has a slightly different refractive angle. He published his first scientific paper in Transactions of Royal Society in 1672. Instead of acceptance, he received strong criticism, especially from Robert Hooke. Hooke was an influential member of the Royal Society, famous for exploring the microscopic world. Hooke had published A Wave Theory of Light before Huygens, although it was nowhere near as elegant. Hooke accused Newton for holding the doctrine that light is made up of a physical material, as Descartes did. However, Newton was not really making such an assumption, at least not yet. He was merely reporting on his observation about the colors of light and could not understand why there was so much opposition. Because of the bad reaction to his first publication, Newton was unwilling to publish any more paper for many years to come, but he kept working on his experiments and making them more refined. His goal was to understand light by deconstructing it into its constituent colors. Newton designed many experiments using the prism, demonstrating that different colors of light have different refrangibility, or refraction indexes. Then he separated them, magnified the effect, and measured them carefully. When light passes through the glass of a lens, each color of light becomes focused on a slightly different location. Therefore, no matter how accurate the shape of the lens is, the focal point will be skewed for each color. Newton discovered this through a characteristically contrarian motivation. Quote, "The imperfection of telescopes is vulgarly attributed to the spherical figures of the glasses, and therefore mathematicians have propounded to figure them by the conical sections. To show that they are mistaken, I have inserted this proposition." End quote. Newton, page 82. Newton then proposed to use mirrors in the telescope to make them more accurate, and also much shorter, a major breakthrough. Newton tried to understand colors step by step. They are not coming from various degrees of intensity of light. Once a color ray is separated, it won't turn into another color by further reflection and refraction. Different color rays can, however, be recomposed to make compound colors and white light again. We now know that the color of objects comes from how they reflect a certain color of light. Everything in Newton's dark room was carefully designed to study the colors of light. But then there was a small observation that made him curious. If two prisms were put together tightly, with two flat walls touching each other, you could see tiny bands of color appearing similar to what you can see on the surface of soap bubbles. Newton thought this coloration must be caused by the tiny air gap between them and decided to investigate it. He used two lenses and put the flat side of one over the convex side of the other, touching at the center. He could see rings of color alternating with the repeating sequence. Since he knew the shape of the lenses, he could calculate the slight changes in the thickness of the tiny air gap at the position of the rings. Then he used single color rays and observed that each color has its own pattern of being reflected and refracted at certain intervals. He made observations about colors made in bubbles and thin glasses as well. He found that, quote, the rays of the same color were by turns transmitted at one thickness and reflected at another thickness. End quote. There is an image and the description is Newton's diagram describing the fits of reflection and refraction for the monochromatic light on a glass lens. And the source is Newton's optics. Newton conjectured that the difference in the light must be associated with some length of periodic alternation. This led to his first description of the periodicity of the light. Quote, every ray of light in its passage through any refracting surface is put into a certain transient constitution or state, which, in the progress of the ray, returns at equal intervals. End quote. Newton concluded that light comes in fits of easy reflection and easy transmission. The distance between the fits corresponds to the wavelength of light. Aside from explaining the color of bubbles, this description of the periodic length of light solved two other problems for Newton. First, it explained why the surface of dense transparent objects, such as glass, always reflect a portion of the light. It's because some light rays happen to be in their reflective fits when they arrive at the surface, and thus reflected easily. Second, it explains why opaque objects, such as a gold leaf, can become transparent if they are sufficiently thin. This is explained by assuming that the entering light ray passes through the medium within one length of its easy transmission fits. Keep in mind, this idea of fits of easy reflection and easy transmission as it holds a key to understanding matter, which will be discussed in the last chapter of this book. Newton's experiments are designed with utmost care and attention to the details. More than that, Newton is entertaining as he describes both his process and his motivation. However, when Newton gets into hypothetical explanations, he is not so careful. For example, he claims that the refraction indexes are related to the density of the transparent objects, but his own table of measurements obviously shows a large deviation for many materials. Then he argues that light must pass at greater speed inside the dense transparent objects based on the assumption of some mechanical forces between light and the objects. He doesn't give any mathematical explanation, but instead claims that speed must be higher, quote, as mathematicians will easily understand, end quote. He also avoids discussing the possible reason for the total reflection when the angle of incidence is larger than the critical angle. The next set of experiments did not start with prisms or glasses. Newton noticed that when light passes through a very tiny hole, the shadows of objects seem a bit larger than they are supposed to be. In one of his experiments, a strand of hair was placed in front of the point light source, and a piece of white paper was held at a distance where it could be brought closer to or further from the hair. One guiding principle of optics, as Newton understood it, was the fact that light rays move in straight lines, so the shadow of the hair should have grown larger linearly when the paper was taken further away from it. However, to his astonishment, it comes to pass that the shadow of the hair is much broader in proportion to the distance of the paper from the hair when paper is nearer the hair than when it is at a great distance. End quote. Another curious observation in the room with a tiny light inlet was the presence of parallel fringes or bands of colored light around the shadows of all objects. In another experiment, Newton used two knives to further control and cut the trajectory of the light beam coming through. And when the distance of their edges was about 400th part of an inch, the stream parted in the middle, and left a shadow between the two parts. Then he placed his prism in front of the light inlet and tried the shadow experiments for each color of light and found that fringes happen for each color with different intervals of brightness and darkness. It would be exciting to see how Newton takes the next careful step and presents other curious observations. But Newton's treatise and its fascinating experiments stops abruptly. He explains that, when I made the foregoing observations, I designed to repeat most of them with more care and exactness, and to make some new ones. But I was then interrupted, and cannot now think of taking these things into further consideration. And since I have not finished this part of my design, I shall conclude with proposing only some queries in order to a further search to be made by others. After the experiments, the queries begin. The queries are a series of suggestions wrapped in question format. Query 1. Do not bodies act upon light at a distance, and by their action bend its rays, and is not this action strongest at the least distance? Newton was trying to understand the origin of fringes on the edges of shadows. He assumed that the fringes and shadows were caused by a mysterious interaction by which objects repel and bend the beam of light away from themselves. More than a century later, Thomas Young showed that these are light interference patterns, very closely related to constructive and destructive wave patterns that Huygens had used in his theory. The queries of Newton are only questions for further research and are not to be taken as conclusions. Nevertheless, The queries start by being more speculative at first and turn more suggestive and authoritative towards the end. At the same time, there is a notable contrast between the precision of the experimenter in the previous sections and casualness of the theoretician in the queries. Newton ultimately proposes two completely opposing ideas about light and ether that must be understood in the context of the thought evolution of Newton himself. Newton's first hypothesis Newton's first hypothesis about ether is presented within queries 17 to 22. Quote, if a stone is thrown into stagnating water, the waves excited thereby continue some time to arise in the place where the stone fell into the water. End quote. Here Newton uses the wave analogy between colors of light and pitches of musical sounds. The fits of reflection and refraction in light are similar to the wavelength of such vibrations. These same light vibrations carry heat energy as radiation and pass through the vacuum space above a mercury column. This means that the medium of light fills the vacuum and the space between the particles of matter. The refraction is caused by a change in the density of the quote, ethereal medium. End quote. When light is entering a glass from air, it is as if it is going from a denser ethereal medium to a less dense medium. Quote, and is not the density thereof greater in free and open spaces, void of air and other grosser bodies, than within the pores of water, glass, crystal, gems, and other compact bodies? End quote. For Newton, the gross bodies, which we know today as atoms, were not the only form of matter that could exist. Ether itself is a kind of matter, but much smaller than the atoms, so that billions of ether particles fill in the gaps of the atoms of gross matter. Why did Newton suggest that ether must be less dense inside the gross matter than in empty space? If he believed that, he could have correctly realized that light as a wave should move faster in air than in water or glass. The problem becomes more understandable by using the analogy of sound waves again. Sound travels in air at a speed that is a function of density, temperature, and pressure of the air molecules. The denser the air becomes, the faster the sound travels. The speed of sound in the air is about 343 meters per second. In water, the speed of sound is 1,433 meters per second. In stainless steel, the sound wave travels at 5,000 meters per second. Beryllium has one of the highest speed of sound at 8,880 meters per second. Waves propagate faster in denser mediums than sparse mediums. The stiffer and more densely packed the molecular structure, the faster they can propagate the disturbances. So far everything makes sense, but in comparison, the speed of light is 300 million meters per second. We need to imagine a substance that is 60,000 times more compact and more stiff than stainless steel. To give an additional twist to the understanding of ether, consider that the speed of propagation of light depends on its medium. The speed of light is not always 300 million meters per second. It passes through the glass at around 200 million meters per second, which is almost a one-third reduction in its speed. In diamond, the speed of light is about 125 million meters per second, almost 2.5 times slower than in the air. This is a significant reduction in speed, but we just explained that waves propagate faster in more dense mediums. How could diamond be actually 2.5 times less dense than the vacuum? Unless Newton was suggesting that perhaps matter is a relative emptiness of ether, similar to a bubble. This concept will be discussed in the last chapter of this book. For Newton, Descartes, and Huygens, it was not difficult to imagine that matter can pass freely through ether. They understood that ether particles are so tiny and yet moving at such great speed that allowing matter to pass through them is not a problem. It is actually much easier than passing through the air. However, for most contemporary researchers who were trying to understand mechanism of ether, this is one of the early problems that challenged their understanding. How is it that the normal movement of matter at regular speeds does not disturb the ether at all? An elegant demonstration and an intuitively physical explanation of etheric fluid dynamics was given by Sir William Thomson, Lord Kelvin, born in 1824 and passed away in 1907, in a lecture titled "The Wave Theory of Light," delivered at the Academy of Music in Philadelphia in September 29, 1884, and published between 1909 and 1917 in the Harvard University's 5-foot shelf of books. Lord Kelvin uses the analogy between light and sound waves to demonstrate his idea. Quote, "I move through this luminiferous ether as if it were nothing, but were there vibrations with such frequency of light in a medium of steel or brass, they would be measured by millions and millions and millions of tons action or force on a square inch of matter." End quote. Here I represent my understanding of Lord Kelvin's model of ether, which correlates with Newton's speculations about the ether in format that can be better understood with our contemporary knowledge and language. Today, we know that air molecules at room temperature move at an average speed of 500 meters per second, which is comparable to the speed of sound at around 300 meters per second. Each tiny molecule moves freely in a small area with such a great speed and bumps into other molecules. Yet, the time scale of movements for molecules of air are much different than a hand moving in the air. For air molecules, adjusting to the movement of our hand does not take much time. Yet our hand sets them in large-scale motion and exchanges momentum with the air. Now imagine ether as a fluid made up of particles that must be much smaller, much more compact, and move much faster than air molecules. The time scale of movements of ether particles are beyond our ability to measure or understand. Their dynamic properties could be much different than anything we are familiar with. To demonstrate the effect that time scales have on fluid motion, let's imagine a glass filled with tonic water on a table. Bubbles of carbon dioxide are forming at the bottom and on the walls of the glass. Also imagine that we have a high-definition camera that can capture the motion of liquid as well as bubbles, and we film the movement of a single bubble that is detached from the bottom of the glass and moved to the surface. Let's say that it takes 1 second. When the air bubble moves to the surface, it disturbs the water in the glass a little bit, causing tiny motions in the water. If we have threads of color added to the water, we can observe this motion. Now, let's have a second glass, filled with a more dense and viscous liquid, honey, with some air bubbles in it. We take another camera and film the movement of these air bubbles through the glass of honey. This time, we keep filming for a whole day, or maybe a month, until one bubble of air gradually comes from the bottom to the surface of the honey. Now, if we speed up the second film to match the speed of the bubble in the first one, we notice a difference. In both films, a bubble ascends to the surface of a liquid in equal time. In the case of tonic water, the bubble accelerates towards the top and sets the water in motion. But in the case of honey, the fluid seems to remain at rest the entire time, while the bubble passes through it at constant speed. The molecules of honey have all the time they need to remain in equilibrium, readjust themselves, and maintain their position. The bubble of air in honey does not disturb the rest state of the honey and doesn't seem to be exchanging momentum with it as it ascends with constant speed. If particles of ether move with a speed comparable to the speed of light in a much smaller space than an air molecule fits, then they are behaving in a totally different time scale. The change in time scale can account for the seemingly absent exchange of momentum between matter and ether. For ether particles, the regular motion of atoms must be extremely slow and boring. They can pass through or around the atoms without any need to exchange momentum with them, and they have all the time they need to maintain their equilibrium. An interesting byproduct of this model is that we may find a linear relation between the size of honey bubbles and their acceleration in honey. Could this be the origin of mass and inertia in Newton's second law of motion? Ether has to permeate all matter. It has to fill the space between atoms, the space between objects, the space between planets, the space between stars, and the space between galaxies. It must be denser in the empty space and sparser where gross matter is gathered. When you look at the night sky, you see a full universe with tiny patches of low-density areas, or stars, that are emitting light. Newton also thought that this differential density in ether could push matter towards each other. He asked if we could describe, quote, every body endeavoring to go from the denser parts of the medium towards the rarer, end quote. Newton initially suggested that the density of ether could explain gravity. This also meant that not only us, but all the planets and stars seemingly pass through ether with ease. Newton's second hypothesis. Newton's second hypothesis is added later through queries 28 to 30, and it is the opposite of everything proposed in the previous hypothesis. By the time he got around to writing his second hypothesis, Newton had completed his Principia Mathematica and perfected his measurements and descriptions of the movements of celestial bodies. He found that gravity is perfectly described by the inverse square of the distance between masses and does not need any further explanation. He found the term "action at a distance" a satisfactory placeholder for any description of why or how gravity works, and applied the same approach to his earlier speculations of the nature of light. Query 28. Are not all hypotheses erroneous in which light is supposed to consist in pression or motion propagated through a fluid medium? For in all these hypotheses the phenomena of light have been hitherto explained by supposing that they arise from new modifications of the rays, which is an erroneous supposition." Newton emphasizes his interpretation of the Huygens experiment with Iceland crystals, which gives us the information we know about the polarization of light today. He argues that whatever happened in the crystal is not a modification of light, but an "original and unchangeable disposition of the rays." There must be an inherent attribute or property of the light that has only been revealed. This is Newton's main argument for the existence of corpuscles of light, since only these particles can carry the unchangeable properties of light by having multiple facets or shapes. "All bodies seem to be composed of hard particles. Even the rays of light seem to be hard bodies." Newton reverses his theory about the low resistance of ether and argues that fluid resistance is only a function of its density, and since ether is dense, it is not possible for it to allow matter to pass through it with low resistance. "If the heavens were as dense as water, they would not have much less resistance than water. If dense as quicksilver, they would not have much less resistance than quicksilver. If absolutely dense, or full of matter without any vacuum, let the matter be never so subtle and fluid, they would have a greater resistance than quicksilver." And finally, we arrive at Newton's corpuscular theory of light, which is really just another question. Query 29. Are not the rays of light very small bodies emitted from shining substances? Hence these particles are capable of passing through "vacuum" in a straight line, and anything that happens to them happens through action and reaction at a distance with particles of matter. This picture is a lot more compatible with the world described in the Principia. He went on to even subvert his own discovery about the fits of light and ascribe the colors of light to the size of these particles. "Nothing more is requisite for producing all the variety of colors and degrees of refrangibility than that the rays of light be bodies of different sizes." I wish I could give this chapter a different title other than Newton's corpuscular theory of light. Here I can finally reveal to you that the title of this chapter comes from a general misunderstanding of Newton's contribution rather than the reality of his assertions. It would have been more fair to remember Newton for his work on the decomposition of colors of light. exploring the periodicity or fits of light, and observing the fringes around the shadow lines from point sources of light. But, with his final reversal and suggestions in the queries, his most influential legacy remains that of supporting the corpuscular theory of light. It is rare to find any reference to Newton's speculations about ether in his first hypothesis and early queries. End of chapter 6. Chapter 7, page 55. Young's uphill battle. Thomas Young, born 1773 and passed away in 1829, was a British scientist, physician, and physicist. When he was still a medical student, he found that the eye adjusts the shape of its lens to dynamically focus objects on the retina. In 1801, he was assigned as the professor of natural philosophy at the Royal Institute, where he gave 91 lectures on then up-to-date concepts in physics. He is particularly known for introducing the modulus of elasticity, advancing the knowledge of harmony in acoustics, and deciphering Egyptian hieroglyphs. Deep understanding of these topics and the problem-solving capabilities was the right combination needed for unlocking the mystery of the light. Young gave 3 lectures on the subject of light and published them between 1801 and 1804 on the theory of light and colors, an account of some cases of production of colors not hitherto described, and experiments and calculations relative to physical optics. He started by quoting Newton and was able to make a case for the wave theory of light using Newton's own experiments and measurements. Young chose his terminology carefully, preferring the word undulations over wave or vibration. Wave and vibration each imply a continuous and repeating motion back and forth that requires a cyclical force or exchange of momentum to be maintained, whereas undulation is only the effect of such motion in a medium. For example, when you strum a guitar, the strings vibrate, causing undulations in the air that manifest as sound. Once a source generates disturbances in a medium, the vibrations are passed on to the medium, and undulations take on their journey in the medium without requiring a continuous connection to the source. This seemingly mundane distinction will become critical in later chapters when we examine the constancy of speed of light. It has been long established that 2 beams of light can cross and pass through without affecting each other. One might wonder why corpuscles of light do not collide at such a high speed of light in the corpuscular theory. But in the context of wave theory, it is easy to understand as light beams are propagating undulations in different directions, similar to sound. For Newton it was not clear how the constituent colors of light can be decomposed and recombined without getting mixed up into a single wave or undulation. That is the original reason why Newton was inclined to assign different types of corpuscles to each color. Young explains how undulations can participate in decomposition and reconstitution of white light without any problem. As an expert in musical harmony, Young knew that sound undulations at different frequencies do not interfere with each other unless They are at a resonant frequency. A musical chord can be heard as a single sound, but a well-trained musician can still hear several distinct notes or overtones in it. There is a somewhat similar explanation for the perception of colors of light and how it interacts with the retina in our eyes. Multiple color receptors in our eye can be excited at once, giving us the perception of mixed colors and white light. Young pioneered the correct assumption about the color receptors in the human eye, which was later completed and confirmed by Hermann von Helmholtz. Young understood that Newton's fits of easy reflection and easy refraction represent wavelengths of different colors. He used numbers reported in Newton experiments on thin plates to correctly calculate the wavelength and frequency of different colors of light. At the resonant frequency, the sound undulations magnify or cancel each other with specific patterns. Young looked for the same phenomena in light and established the fundamental principle of interference. Equipped with this additional knowledge, Young was able to explain Newton's observations in the dark room with a single point of source. Young replicated Newton's experiments of shadow of a hair, two very close knife edges, and colorful shadow fringes, among others, in the dark room with a pinhole light source. All the anomalies could be explained by light interference. The interference was obviously seen when Young added a second pinhole source of light in the room. The constructive and destructive wave patterns were undeniable evidence of wave behavior. There is an image and the description says, patterns of light interference caused by two-point sources of light, reproduced from Young's article. Today, we know that light interference is responsible for the colorful wings of insects, colorful patterns on feathers of peacock, and colors of bubbles of soap. The soap bubble colors were carefully observed and their succession was accurately recorded by Newton. The interference explains them as constructive and destructive interferences from the two reflected light waves coming from each side of the tiny layer of the bubble. Imagine a white light shining on the bubble. First, some light is reflected from the outside of the bubble. Then it passes through and reaches the inner side of the bubble and gets reflected again. These two reflected lights come back to our eyes together. If, for example, the two reflected lights have a phase difference equivalent to the wavelength of red light, then the red color will be eliminated because of the destructive interference, and the light would appear blue-green. These phase differences are a function of the thickness of the bubble, thus creating different bands of color. The bubbles sitting on a flat surface usually have thinner skin on the top compared to their sides and bottom. At the very top of a soap bubble, the thickness of the bubble can become as low as the size of blue wavelength, where reflected light appears yellow. Beyond that, the bubble can become even thinner than any visible wavelength of light. In such cases, the bubble top is less than a few hundred nanometers thick and is ready to pop. However, it was observed by Newton that the thinnest layer of a bubble always appears to be black over a black background, as if it does not reflect any incoming light. Young understood that interference explains the bands of color in bubbles, but he did not yet know why it was that whenever the thickness of the soap bubble is less than the wavelength of light, the interference becomes destructive. Some mechanism has to create an exact half-wavelength phase difference between the two layers of a bubble for all colors of light. When a wave propagates from a more elastic to a less elastic medium, some of it gets reflected and gets inverted in shape. It is similar to what happens when you send a pulse along a rope tied to a wall. The returning pulse is upside down. That must be the light reflected from the outside layer of the bubble. So the water of the bubble must act as a retardant for the light that is passing through the air. There's a schematic, and the description says the schematic view of a destructive interference on the thin layer of soap bubble up compared to the constructive interference bottom. Young produced a constructive interference pattern using two types of glasses and a thin layer of oil between them. Young must have observed that if the law of interference is correct, then it should dictate a single answer to the old question of whether light moves faster or slower in a medium that is more refracting. The wave theory of Huygens predicted that light must move faster in the air than in the water, and the corpuscular theory of Newton had predicted the opposite. Young started to work on an explanation based on the law of interference. Quote, in applying the general law of interference to these colors, as well as to those of thin plates already known, I must confess that it is impossible to avoid another supposition, which is a part of the undulatory theory, that is, that the velocity of light is the greater, the rarer the medium. End quote. Young conjectured that if his interpretation is correct, then by inverting the ratios of refraction of bubbles at one of its sides, the opposite effect should be produced. This means that a very thin layer made out of materials that is less refracting than its inside and more refracting than its outside environment should have the opposite behavior of normal water bubbles in air. The inverted bubble should produce a white spot at its thinnest thickness, reflecting all the light by constructive interference. So he made such an inverted bubble by, quote, interposing a drop of oil of sassafras between a prism of flint glass and a lens of crown glass. End quote. Apparently, the refraction index of the oil is between the two types of glasses, and when the glasses were pushed together to reduce the thickness of the oil layer, Young observed the bright spot at the thinnest layer. With this experiment, Young gave the first experimental proof that the speed of light is higher in air than in water without directly measuring them. Thus, Young calculated the wavelength and frequency of colors with an accuracy that stands correct today. Using the law of interference of light, he explained the additional color producing experiments that had not been accounted for before, and finally he announced, quote, I am disposed to believe that the luminiferous ether pervades the substance of all material bodies with little or no resistance, as freely perhaps as the wind passes through the groves of trees. End quote. Young answered Newton's criticism of Huygens' wave theory in every account except the extraordinary refractions in doubling the Iceland crystals, to which he replied, quote, Huygens' most elegant and ingenious theory perfectly accords with these general effects in all particular, and of course derives from them additional pretensions to truth. This he, Newton, omits in order to point out a difficulty for which only a verbal solution can be found in his own theory, and which will probably long remain unexplained by any other. End quote. Young's criticism of Newton did not go well with the established science of the day. He received immediate rebuttal and negative reviews from the guardians of the temple of science, especially from an anonymous author in the Edinburgh Review. Quote, We wish to raise our feeble voices against innovations can have no other effect than to check the progress of science, and renew all those wild phantoms of the imagination which Bacon and Newton put to flight from her temple. End quote. For about 15 years, Young remained the only prominent scientist who defended the wave theory of light. Others were reluctant to abandon Newton's corpuscular theory. According to I. Bernard Cohen in the preface to Newton's Optics, quote, had not Fresnel and Arago in France become interested in the work of Young, it seems probable that the influence of the great name of Newton would effectively have blocked any pursuit of Young's idea, at least in England, and any further development of the wave theory of light. End quote.